Welcome to our 34th session. In this session, we're going to start Chapter 18, which is, I believe, called Corrections to the Simple Model. We'll be looking at both the qualitative and the quantitative aspects. The quantitative is going to involve a little bit of mathematics, but we'll deal with it and we'll get through with it. The qualitative is going to be, for the most part, a review of what we've done in the last number of sessions. Then we'll be examining the quantitative model, focusing in on the regions of the MOS structure, the right regions, referring to the accumulation, the depletion, weak and strong inversion, and then we'll be focusing in on the depletion and inversion charges, and that's going to be the subject for the next few sessions. But before we get started, I'd like to share with you a marvelous clip from Schubert's Trout Quintet. Welcome back. Here are some of the topics we'll be covering in today's session. We're going to start off, we already have the trout, and we're going to start off with a qualitative discussion of the simple model. That'll be mostly a review, and then we'll go on to the quantitative, and forewarned, there's a bit of mathematics here. And then we're going to use those formulas that we derive to talk about the regions of the MOS structure, and of course that's the old story of the accumulation and the depletion and the weak and strong inversions. And then we're going to do a little bit more depth on the two important regions, which are the depletion and the inversion. And finally we're going to develop a relationship for the inversion charge. So let's get started with a review. We started this last time. This is the simple equation. The inversion charge starts at threshold. When the gate voltage is equal to threshold, this says the inversion charge is 0. And that is wrong. And we know it's wrong. But that's what we basically have in our undergraduate courses. Okay, we need a relationship between charge and voltage, and of course that is the basic relationship, which says that charge Q is equal to capacitance, in this case oxide capacitance, multiplied by voltage, and it's the voltage above threshold. Okay, so this was the figure that we started to look at last time. This is for a doping of 10 to the 17th. We know that because the bulk potential is 0.42 eV. It's measured from intrinsic to the Fermi level. We could also have flipped this bad boy around and measure it from the Fermi level to the intrinsic, and then we call it the Fermi potential. But that's really not terribly important right now. In this particular case, we are not at threshold, we are at intrinsic. So there really is no inversion charge at all at the surface. However, if we increase the gate voltage, make it more positive, this guy will bend down further and further until we do go into strong inversion. And at that point, there will be a layer of inversion charge from the source end. Let me start here. From the source end, which is over here, to the drain end, which is over here. Now, what this figure does is it takes this energy band diagram and it rotates it 90 degrees so that Y now becomes horizontal and X becomes vertical. X in this case would be down. Rotate this by 90 degrees clockwise. This arrow points down, so X points down. Y points from left to right. So we're going from the bottom here, which is the source end, to the top, which is the drain end. And the reason that I make this cut here is because when we do something very strange, actually it's not strange, it's essential for the working of the device, we're going to put another potential. Here we have the gate potential, and that's fine. That's what causes the band bending. But we're going to put another potential between the drain end. We're going to make the drain end positive, and the source end we're going to ground, so that now there's going to be two potentials, one in the Y direction and our normal conventional one in the X direction. The nice thing about it is they don't interfere with one another, and that's one of the principles. We'll talk about that a little bit later. But here's the deal. When you have strong inversion and you have a layer of inversion charge and you put a voltage at the drain compared to the source, the energy band diagram will change depending upon where we go along the gate. So if we go here, we'll have one energy band diagram. If we move this dotted line over to here, or if we move the dotted line to the right, we'll have a different energy band diagram. And when I say a different energy band diagram, the band bending will be different. And that is absolutely essential to the way that this device works. For example, this is what we'll see. We can have strong inversion at the source end, and we can have essentially intrinsic, or, well, not depletion, but we can have very weak inversion at the drain end if we have a strong enough positive voltage. So on one end, band bending is quite severe or nice, lots of inversion charge. The other end will have just a little bit of band bending, and that is a big deal. So that's an essential part of the way this thing works. Okay, so let's take this a little bit further. This again is going to be very much in the way of a review. We start with a p-doped silicon. That will be our standard or default position, doped to 10 to the 17th. That's what's depicted in the figure, just entering into inversion, weak inversion. So it's just barely intrinsic, so phi will be 0.42. What is N0? For doping of 10 to the 17th, N0 will be 10 to the 3rd. And if we put in 0.42, and we perform this rather straightforward calculation, we get exactly what we would have expected, 10 to the 10th electrons at the surface. So in this particular case, we have 10 to the 10th electrons per cubic centimeter, and that is extremely small. That is essentially nothing. Okay. And we can develop the equation 18.4 is really rather straightforward, to say the least. It just says the doping for 10 to the 17th is, well, 10 to the 17th in the bulk. That's all. It says P0 is equal to the doping level, 10 to the 17th. The only assumption here is that Boltzmann statistics apply. We know it's Boltzmann because this is not the Fermi-Dirac function. It's the simple Boltzmann relation. So, of course, Ni is 10 to the 10th, and then here we have phi b is 0.42. Okay, so we put these two guys together now. We can rearrange A2 by basically taking this over to the other side, and that's all we're doing here. Then we know that the answer by the intrinsic level is the doping level with a minus sign. Notice this minus 0.42, and then N0 will be Ni. Again, e to the minus phi b q over kt. I put the q's in here. Sometimes I forget, sometimes I don't forget. It really is not terribly a big deal, either way. Okay, so we combine these two equations. This is what I'm looking for. I don't care about N0. It's pretty straightforward. I don't care about Ni. I don't care about Na. I want to know how many electrons are there at the surface. And the number of electrons at the surface is equal to the equilibrium N, or N0, which is 10 to the 3rd, multiplied by the Boltzmann factor. And here the phi is the phi at the surface. I could have written this phi sub s, many people do. I know it's the surface because I've said surface. And then I just basically substitute for N0 using equation 18.5, and I get equation 18.6. And that's pretty straightforward. If we have phi is equal to phi b, this goes to 0, and that means that the surface will have the intrinsic value. So if the surface is equal to the bulk, way back here, that's what we have here. The surface, the band bending, is equal. This is the band bending phi at 0 at the surface is equal to the bulk. Then I have intrinsic. That's all this thing says. Where is it? Someplace here. Gotta be here someplace. Okay. Here. However, if phi is greater than phi b, in fact, if it's 2 phi b, then I will have an A. And that's what we show here someplace. Okay, now right here, if phi is equal to 2 times the bulk, then I will have basically the bulk here. So I'll have Ni 10 to the 10th multiplied by e to the 0.42 divided by kt. So N surface, in that case, would be N sub A. So if phi is equal to 2 phi b, then the surface charge will be equal to the doping density, or 10 to the 17th, and that is threshold, more or less, that is the onset of strong inversion. So this is the basic equation. Everything is things that we've seen many times before. We just go through some relatively simple examples here. If phi is equal to 0, there's no band bending, and of course the surface comes back to what we expect, which is the equilibrium value. And there's two more cases. There's from flat band to intrinsic, and we basically covered that in our simple example. So you can, I shouldn't say simple, straightforward examples. I hope they're straightforward. So you can just read that over, and it's basically everything we've said. And at threshold, we have 10 to the 17th, because phi is equal to 2 times the bulk. And that's why this goes to 0 here, and we get the surface is equal to N sub A. And that's basically illustrated by this figure here. If we look at the surface amount of electrons per cubic centimeter at the surface, in depletion, essentially nothing, and then we get phi is equal to the bulk, or intrinsic, that's 10 to the 10th, and then we creep up a little, and right somewheres in this region, we're at threshold, and then above threshold, zoom, it shoots way up. So that's basically what we're saying there. So that's all there is. There is an exponential increase in negative surface charge, which is to say electrons starting from intrinsic, continuing through weak inversion until threshold. It just takes off. That's characteristic of exponentials. They start out slow, but once they get going, kazoom, they really take off. Okay. Now we are ready to tackle, with no fear or trepidations, we will tackle the corrections to the simple model quantitatively, not just qualitatively. And we begin with the basic tool in our toolbox, which is Poisson's equation. Notice I didn't include signs here. I'm not interested in signs. I'm interested in relationships. So I'm sloppy with signs anyway. I'm sloppy with constants. If they don't contribute to getting a reasonable answer, I don't worry about it. If I get an answer which is completely unreasonable, then I'll look at constants and signs. In this particular case, rho represents all the charges, special charges, the charges that give rise to electric field. Generally, charges that give I should say almost always, charges that give rise to electric fields are stationary. charges which are mobile in electric fields will move. In this particular case, we're going to look at those charges that can be potentially mobile, but they're static in this particular case. And there are four types. There are holes, there are fixed negative acceptor ions, which have accepted an electron. There are electrons in the conduction band, or actually at the conduction band, but actually at the surface, I should say, of the in the energy band diagram. And then there are donor fixed atoms, which are positive because they've donated an electron and they become positive. So basically we put in the row all the charges into Poisson's equation to get equation 18.11. And the electric field is equal to the first derivative of potential, and the first derivative of electric field is equal to the charge density. So I differentiate the electric field, which is the second derivative of the potential, and I get equation 18.11. Okay, now if all this was equal to 0, and this was a three-dimensional problem, this thing would turn into something called the Laplacian, and the equation would be Laplace's equation. If we have non-zero on the right side, we call it Poisson's equation. This is a relatively difficult equation to solve, and that's going to be our job, to simplify this guy so that we can solve it. Okay. First, the review part. The number of holes as a function of x is equal to the P0, which is the doping concentration, multiplied by the exponential term where the minus sign is important. I didn't include the Q here because I don't think it's important. This is obviously in electron volts. Here we have a minus sign because the number of holes as we move from the bulk toward the surface is going to be reduced. So if phi goes up in a positive sense, this will be a negative term and the number of holes will go down. So if phi is, for example, plus 0.42, then p sub 0 at the surface will be p0. P of x equals 0, I should say, will be p0, which multiplied by e to the minus 0.42 in the exponent. So p at x equals 0 will be intrinsic. And the same thing for the number of electrons. We start out, if phi is 0, we start out with the equilibrium number of electrons, 10 to the third, but as phi goes up, the number of electrons at the surface, specifically at x equals 0, goes up along with it. And if phi at 0 is 0.42, then n of 0 will be also intrinsic. Okay. Now here's the important thing. We're only going to consider a acceptor doping. We're going to let the donor doping go to 0, which is to say we're going to be looking at p silicon. That's all that says. So that's going to eliminate this guy. Now we have 3 charges. Well, that's a good thing. We eliminated a little bit. Okay. Okay, so just one comment here. Of course, P0 is equal to Na, which we know. N0 is Ni squared over Na. And of course, for 10 to the 17th, this is 10 to the 3rd, and this is 10 to the 17th. We let Nd plus go to 0. It is only acceptor doped, and we include one more thing here, which is the thermally generated holes. There are how many thermally generated electrons? Well, if it's 10 to the 17th doping, there are 10 to the 3rd thermally generated holes, and there are 10 to the 3rd thermally generated electrons. The number of thermally generated holes is always equal to the number of thermally generated electrons. The number is quite small if the doping is relatively large. With no doping, the thermally generated holes would be 10 to the 10th. The thermally generated electrons would be 10 to the 10th. So we're going to include this, and it just makes the equation a little bit more pleasant looking, but it's completely irrelevant because this is such a small number that it's not going to affect the results at all. 10 to the third, it's really, really small. But most authors include it because it makes everything look a little bit nicer. So here are the holes. What are they? I just substitute this in here for the holes. This is the thermally generated holes here. This is the N sub A. So you notice here that N sub A changes in sign. It was plus over here because they said, well, it was holes. Holes were positive, but the actual sign of the charges are negative because they're negative fixed signs. That's why I have a minus sign over here. And let's take a look at this a little bit further. It's a little bit misleading. So what I've done is I've actually written it out here. There are 4 terms. 1, 2, 3, 4. First, these are holes which decrease because generally we're going to let phi become more positive. Of course, if phi is negative, these guys will increase. That's accumulation. But phi is going to become, we hope, if it's going to be a useful device, phi is going to become more positive, and therefore this component will decrease as we go toward the surface. Let's see, what is the second are the negative fixed acceptor ions. That's this guy over here. The third, this is a really important term, these are the electrons at the surface, and these will not start to kick in until phi becomes really, really big, because this term here is really, really small. This is 10 to minus 20, this is 10 to 17th, so this is pretty big, pretty small. So, and this term is these guys are the thermal, that's plus N sub A over, plus N sub I squared over NA, that's this term here, and that is negligible. So these are the 2 terms we're going to be concerned about. And of course we want to solve the equation, which ain't easy. Before we do that, do the same thing, exactly the same thing for a donor doped. And if we do that, we get exactly the same form. We have 4 terms. Notice that the forms are precisely the same. The only difference is the signs. And we have a minus sign here, we have a plus sign. Signs are reversed. So if you go through this, I think you'll get something that looks like this. And of course we could solve that for a PMOS or a N-type substrate. But we're going to solve it for the P-type. Well, we have a problem with equation 1812. So if you look at 1812, first thing is there's 2 integrations because it's a second order derivative. We have to integrate with respect to x once, and then we have to integrate with respect to x twice. The problem is that I don't know phi as a function of x. So this is a one unholy mess, unless I'm clever. Well, not me personally, I'm not that clever. But people looked at this and said, we have to change this. We've got to make this into a form which I can integrate. And the way we do that is that we change the variable. We need to change the variable from x to phi. And that's what we do here, and we use the chain rule. So the chain rule says that if we have a function of a function, function f of a function g of x, and we want the derivative of this function with respect to x. What do? We take the derivative of the function f with respect to g, and then we take the derivative of the function g with respect to x. And if you're a slob like me, most engineers will just cross out the dg terms to produce a derivative of f with respect to x. So this is kind of obvious the way it looks. This is what we're going to use. So I give a little example here. Suppose we have the function g sub x, which is equal to the sine, and I have the function f of whatever is the square. So whenever I put in here to get f, I square it, and g is the sine. I want the derivative of f of g with respect to x. What do? I take the derivative of f with respect to g, which is f with respect to g, which is just 2 sine x. So this term here, 2 sine x, is this term. Derivative of f with respect to g, and then I take the derivative of g with respect to x. Well, it's the derivative of g, which is sine of x, with respect to x, which is the cosine of x. So the derivative of the sine squared of x is equal to 2 sine x cos x. That's something one learns in elementary differential calculus, but we're going to use it, so that's why I repeat it. In our case, the function f is some function squared. What is that function g? We're going to let g be d phi dx. In other words, the electric field. That's all this is. D phi dx is the electric field, and what we have is d phi dx. We're going to square it. Now, that's not what we have here. That's kind of a way station. They say, let's consider this guy right here. And we do exactly what we did here. We take the derivative of this, which is 2 times the function. This is the function g. We bring down the 2, write the function g, and then we take the derivative of d phi dx with respect to x. Exactly what we did here, except instead of sine, we now have d phi dx, and if we take the derivative of d phi dx with respect to x, we get the second derivative. This is the term right here which we are interested in. So we just take all this good stuff and we slam it over to the left side. The 2 becomes 1/2. We flip this guy. This becomes dx d phi, and then we just rewrite d dx of the second derivative. Now, I'm very cavalier, very kind of sloppy. Now, just like I did up in here, I cancel numerator and denominator. So here I cancel the dx here, and the dx here just goes away, and I have 1/2 d phi of the second of the electric field squared. This I can integrate. What I've changed now from a variable of x now to a variable of independent variable phi, and I have the electric field squared, and that is really nice. So I put all that stuff in, and instead of solving this equation, of course I should say the nt is 0, I have this equation 1815, and I integrate now with respect to phi. The electric field squared. If I want the electric field, which is what I'm going to be solving for, then I take the square root. The important thing is now I'm integrating over phi. And that is a super, super big deal. And of course, again, d phi dx is just the electric field. And I didn't want to go and explain why there's a minus sign. So I'll just drop the minus sign. It's not a big deal. Okay, so many times you write beta. Actually, beta is really q over kt. I'll write it over kt. You can put the q in or not, again, as you wish. It's not terribly important. And what I'm doing here is basically reiterating things. This is a pure review. All I'm saying is that as phi gets more positive, P0 goes down and N0 goes up. And that's all that is. Carrying out the integration, really straightforward, because exponentials integrate to exponentials, ones or constants integrate to linears. So I've got a bunch of terms here. Actually, there'll be 6 terms. Okay, so actually just one little correction here. I had this at phi of this function of x. This is actually at x equals 0. So I just corrected that. So again, here is the result of the integration, the 6 terms. The minus 1 again comes from integrating the exponential, and at the lower end phi is equal to 0, and of course e to the 0 is 1. So that's where we have this term and we have this term. We have linear terms which come from integrating the minus 1 up here, gives us a linear. At the lower value of that linear term, of course, we get 0. And that's why instead of having 8 terms, we have only 6 terms. And one other thing, we will have the electric field. Gauss's law says whenever there's an electric field, there must be charge that produced it. And of course, whenever there's charge, the charge results in an electric field. And there is a proportionality between charge and electric field, the constant of proportionality being a material constant, the permittivity. And you can look at it as simply a proportionality constant or something that just makes the units come out right. The units of charge are going to be in coulombs per square centimeter. And now our job is to simply transform the electric field into charge. Because again, charge is the name of the game. Charge is what we're interested in. Specifically, we're interested in the inversion charge, the charge between or at the oxide semiconductor interface. And of course, charge is related to voltage by C-ox, and C-ox is the areal oxide capacitance in farads per square centimeters. So Q is also going to be in coulombs per square centimeter. And I just have a little short blurb which proves that. And we get that surface charge is not in coulombs, but in coulombs per square centimeters. And I put all that stuff into this equation 817. Up here, there's an epsilon which from here, which flips this epsilon up into the numerator, and that is an expression. Again, 6 terms. Haven't changed the number of terms, haven't changed the terms. All I did by using Gauss's law was to change the units of the coefficient. So here we have an expression, and this is our basic expression now for the surface charge at the oxide silicon interface as a function of these 6 terms, and the question is which of these terms are important. It depends on the region. Not only that, we'll find that this term is insignificant, This term is insignificant. You have 2 knocked out. This term is insignificant. So we only have 1, 2, 3 terms. So out of the 6 terms, we're only going to be really interested in 3. And that makes our job a heck of a lot easier. So let's look now at the region. First region is probably the easiest one, and that's the one we always start with. That's a flat band. So all the bands are completely horizontal. Phi is equal to 0. Put in phi is equal to 0. Plus 1 here, minus 1 cancels out. Phi is 0, cancels out. 0, 0, 0 here. This is 1, minus 1, that's 0. And of course, phi is 0. So the Q sub s is 0, exactly as we would have expected. Now let's look at accumulation. In accumulation, we have a negative value for phi, so we have up banding up, everything bands up. The Fermi level is now closer to the valence band edge at the surface, and we expect, well, let's see, what do we expect? Phi is negative. This term certainly comes to life. This term is going to be a little bit negative. All of these terms are basically insignificant because this is a really, really small value. So one can argue that this term may have a little bit of an issue, but if phi is even, oh gosh, say 100 millivolts or so negative, this term is going to dominate. And if this term is the only term we're considering, we have a square root, so that is the 2 here, phi over 2 kt. So if we assume that we only have this term in accumulation, then this is the result. It's pretty straightforward. And let's see if that's true. So we're going to test it out by putting in a phi of minus 0.1. That's a band bending up. And let's see what we get. And we get about 7, which is much greater than 1. So this term would cancel out. And 0.1 over 0.026 also is relatively small compared to the exponential term. So we conclude that in accumulation, the dependence of the surface charge in coulombs per square centimeter looks like an exponential. I put the magnitude sign here because we're really interested in the dependence rather than in the sign of the power. Okay. And the interesting thing is we'll see exactly this dependence when we look at strong inversion. And that makes sense because accumulation, the device structure looks like a capacitor, Cox, and at strong inversion, the structure looks like a capacitor with capacitance of Cox. The only difference is there's a depletion capacitance in series in strong inversion, but the dependence of the Q on phi is going to be the same. So in strong dependence, strong inversion, we're going to see this term predominate. Accumulation, this term predominates. Strong inversion, this term is going to predominate. Okay, so let's see one other thing. Let's put in some more numbers into equation 821 to see how much the bands bend up for a given gate voltage. So suppose we have, this is accumulation, we have a voltage of, say, minus 1 volt, assuming flat band is 0. How much do the bands bend up? Is it 50 millivolts, 200 millivolts? Let's see. And we can find that out by simply, doing equation. First equation we have right here. We just rewrite that. And what we have to do now is to, first of all, put in all these numbers. So when we put in all of these numbers, it's a pain in the neck. This is the permittivity of the oxide, KT, in joules. The doping is 10 to the 17th. The 300 is the temperature, room temperature, and that's basically it. So we get 2.9 times 10 to the minus 8th when we carry through the arithmetic here. We also have a relationship between the surface charge density and the gate voltage. So we basically just equate these two. And when we do that, we find that this guy we bring over on the other side, and it's equal to Cox Vg divided by this bad boy right here. And we get that an equation for phi, pretty straightforward. We have to, I should mention, we have to assume a Cox, which means we have to assume a Tox. 100 angstroms is moderate, a little bit on the high side, but it produces kind of a moderate Cox, 3.5 times 10 to the minus 7th farads per square centimeter. And we put all that stuff in, we get about 130 millivolts. And that's a fairly good number. That is for minus 1 volt or 1 volt in the accumulation side of the equation. If we put in 2 volts, we get a little bit more, 166 millivolts. And that is actually kind of important. We go from 1 volt to 2 volts, we only increase the band bending by about 30 millivolts. And if we went to 3 volts, we would increase it a tiny bit more. So there is a diminishing return here. The more we increase the gate voltage, the amount of band bending is pretty much pinned or fixed at probably well below 200 millivolts. So that's all consistent with our qualitative analysis. And it's nice that when we do things quantitatively, we get results which make sense. So it shows that we should be on the right track. Okay, so now we go from flat band, we go from accumulation back to flat band by making the gate more positive. We were at minus 2, minus 3 volts. Now we're going to go back to 0 volts, which is to say flat band, and then we're going to proceed to depletion and to weak inversion. So we go back to our basic equation. All this stuff is going to go away because now phi is going to be positive. So this is basically is going to be all pretty much 0, and we'll be looking at these 3 terms here. Actually, these only 2 terms, because this term, the last term, is going to be completely negligent. So let's do that. But before we do that, we want to tackle one relatively straightforward problem. Just want to show that the Q sub S from equation 821 is indeed in coulombs per square centimeter. We really haven't done that. All of these terms are unitless, so the only term we need to take a look at is the coefficient. And that's what we're doing here. We say, what is the coefficient here? Units of epsilon are farad per centimeter, KT is joules, and NA is numbers divided by cubic centimeters. So we put all that stuff in. First we have to translate farads into more basic units. It is coulomb squared per joule. Put all that in to this term here, and we get coulombs per square centimeter, exactly as we would have expected. That's really pretty good. So we're going to collapse this thing now for depletion and inversion. All of these first 3 terms go away. This term goes away. We have 2 terms, which are right here. And the question is, which one is bigger? And that is our goal, to ask which one is larger. So for relatively small values of phi, I'm going to claim that the second term will predominate, and it's going to work out that this term gives the depletion term, and this term gives the inversion term. and eventually it will dominate when we go into strong inversion. Okay, somewhere there's going to be a transition between this term and this term, and we expect that that's going to occur somewhere around threshold. So we would expect that transition to occur somewhere around 0.9 to 1 volt of positive gate voltage. The threshold for N sub A 10 to the 17th is in that range, and that's what we're going to see. Okay, so we put in 0.2 volts. That's still pretty small, and we expect that the linear term will predominate, and boy, does it predominate. It's about 2.8, whereas the exponential term is 10 to the minus 6th, so no contest. But we know that exponentials always win. Whenever you have an exponential and any other term, no matter what the power is, eventually, if the argument is large enough, the exponential will win. The question only remains, how large is large? So we put in 0.9 volts. We expect that that's going to be close. And if we put in 0.9 volts, we get the linear term is 5.9, but the exponential term now is comparable. And if we go above 0.9 volts for the band bending, then we get a situation where the exponential term at 22 is much greater than the linear term, and this would be what we would consider strong inversion. So we have a complete dominance of the exponential term, despite this incredibly small coefficient. So just 2 points here, which should be reasonably straightforward. First one we already know. At depletion, we have the linear term which predominates, and we're going to return to that in just a little bit. While in strong inversion, we have the exponential term. Now, if you look at this exponential term in strong inversion, and you go way, way back, oh my goodness, somewhere's here, to depletion, we find that it is exactly the same. This is the variation of Q sub S in accumulation, and this is the variation of Q sub S in strong depletion, and they are precisely the same, and that makes really a lot of sense. The difference between accumulation on the one hand and depletion / inversion on the other hand is in the latter we have an extra term which is reasonable. And the second point, which is a little bit less obvious, is it takes much less band bending to invert a lightly doped substrate than a heavily doped substrate. Of course, we know that. That's been something which was, we've said many times, a number of times in the past, and we can see that by this factor right here. It's 10 to the minus 14th for a doping of 10 to the 17th, but it's only 10 to the minus 10th, 4 orders of magnitude less for a doping of 10 to the 15th. So we would expect that this transition from linear to exponential would occur at a much lower voltage. In other words, the threshold voltage would be much lower for a lightly doped substrate, and that is exactly what we find. Okay, it's interesting to look at these results graphically, and if we do that, we find something different than we would find in the very simple model. There is this transition region between depletion and strong inversion, where the charge varies more or less in this fashion, and at the silicon surface we have an extra inversion layer charge even when we are in depletion. So let's look a little bit deeper on to the aspect of the depletion charge and the depletion layer, specifically the depletion layer thickness, the W. And to do that, we go back to our linear term. This is our depletion term. So this is the term that's going to be relevant for depletion. And we go back to the full expression of 821 only for depletion. We're only keeping the depletion term here. So that's this term right here. We're only keeping that term, of course, with a coefficient. And we put in the coefficient, and we find that the dp dx, which is the electric field, is given by 1822. And here I had to put the Q in, which I generally neglect because I want to get a numerical value. So when I do that, bringing the KT over to the left here, the KTs cancel out, so I get 1822. And then we have a differential equation here, relatively simple to follow. d phi equal d phi divided by the square root of phi. Just bring this over to the left side, bring the x over to the right side. Everything else is a constant. So this is relatively straightforward to integrate. Phi to the minus 1/2 integrates to phi to the plus 1/2. Of course, I bring down 2. And then this term just carries over, and the integral of the x is just x. I square both sides, getting equation 1823. And then I ask, what is the depletion width? Well, that's x. X is just W, the depletion width, as a function of phi. So I solve for WD, the depletion width, x, bring this over to the left side, flips, and this is an equation for the depletion width as a function of the potential. Exactly what we found for p-n junctions and for Schottky barriers. So 1824 hopefully looks very familiar. We've seen this time and time again from Schottky's to p-n junctions. Now the maximum depletion width occurs when phi is equal to 2 times the bulk. And phi is equal to 2 times the bulk, and then this is the relationship as a function of n sub a. Putting all that stuff into WD, we find WD maximum, and we carry out the arithmetic here, and we find that it's about 0.1 micron, about 1,000 angstroms for 10 to the 17th doping. That's very, very thin, and the reason it's thin is because the doping is relatively high. If the doping was lower, we would find a much larger WD max, and in fact, for 10 to the 15th, if you put in the numbers, you find it's almost 0.1, almost 1 micron, about 0.9 microns. And we're going to return to this equation when we look at the MOSFET. So this is a kind of important equation. So just one more little topic before we end it up today, finding the inversion charge. Well, we don't know really what the inversion charge is from our basic equations, and really there's no way to tell, because we have in inversion, or in depletion/inversion, we have an interplay between depletion charge and inversion charge. But I'm really interested in inversion charge. So what do? Well, let's see what the depletion charge is. The depletion charge is just the depletion charge density in coulombs per cubic centimeter, which is QNA, multiplied by the width. That will give us the depletion charge density in coulombs per square meter. And we do that, and we find that it's pretty straightforward. We know what WD is as a function of phi, a function of phi, which is right here. And what we do basically is we take our total charge, which is the entire kit and caboodle, and we subtract out the depletion charge. And here is the depletion charge. Well, this still is not a particularly simple thing to evaluate. And what we do is we take this expression right here and we expand it as a binomial expansion. It's 1 plus a small number to the 1/2, which is approximately equal to 1 plus 1/2 times this small number. And we do that right here. And we get that the inversion charge is given by equation 1829. You can carry through and follow through. Hopefully, the algebra it's not terribly difficult. And here I put in the cube. So look for me. I'm so lazy. All right. Well, that basically finishes things up. We will finish our session with a beautiful rendition, a clip from the Dillabé ballet called Coppelia, and we'll see you next time. Enjoy the ballet.